15 to 60 minutes, that is the only warning you get. Not hours, not days. 15 minutes, maybe 60 if you're lucky, before a wall of charged plasma moving at 1,293 kilometers per second hits Earth's magnetosphere and rewrites the rules for every satellite, every power grid, and every communication system on the planet simultaneously. That number is not a forecast. It is not a worst-case scenario pulled from a climate model or a theoretical physics paper. It is the measured velocity of a coronal mass ejection already in transit, already moving, already crossing the space between the Sun and the point where NOAA's Discover satellite will detect it and send the final alarm. By the time most people reading this headline finish their morning coffee, the window will already be closing. By the end of this video, you're going to understand exactly what 1,293 kilometers per second actually means, not as an abstract number, not as a statistic to scroll past, but as a physical event with a specific sequence, a specific timeline, and consequences that scientists have been modeling for decades and hoping they would never have to use in real time. You're going to understand why this particular CME is categorically different from the solar storms that hit Earth every few years, and get a paragraph in a science newsletter. Why the speed alone changes every calculation. Why the warning window is so small, it effectively makes real-time response impossible for most of the systems that need it most. And you're going to understand something that almost no mainstream coverage has touched. The fact that the infrastructure protecting Earth from this kind of event was designed around assumptions that a storm at this velocity fundamentally breaks. We will get to that. Stay with this. Start with the physics. A coronal mass ejection is not a beam of energy. It is not radiation in the way that a solar flare produces radiation, a burst of electromagnetic energy that crosses 150 million kilometers in about 8 minutes. A CME is matter. It is billions of tons of magnetized plasma torn from the sun's corona during a magnetic field collapse and hurled outward at speeds that range from a few hundred to several thousand kilometers per second. The average CME travels between 300 and 500 kilometers per second. At that speed, it takes roughly 3 to 4 days to reach Earth. 3 to 4 days is a functional warning window. Satellite operators can move assets into safe mode. Power grid managers in vulnerable high-latitude regions can reduce load, open circuit breakers, prepare for induced current surges. The military can reposition communication satellites. Airlines can reroute polar flights away from the radiation corridor. 3 to 4 days is enough time to do most of what needs to be done. It is not comfortable. It is not ideal, but it is workable. 1,293 kilometers per second is not 300 to 500. It is not even close. At 1,293 kilometers, a CME covers the Sun-Earth distance in approximately 1 to 2 days. Not 3 to 4, 1 to 2. That is not a 25% reduction in warning time. That is a structural collapse of the response window. Every protocol designed around the average CME speed assumes time that this event does not provide. And the agencies responsible for managing the consequences are not getting that time back. Here is what makes the speed the critical variable, and not just a dramatic headline number. When a faster CME hits Earth's magnetosphere, it does not just arrive sooner. It compresses the magnetosphere more violently. The magnetosphere is Earth's magnetic field, the invisible bubble that deflects solar wind continuously, the same field that without it would have stripped Earth's atmosphere away billions of years ago. Under normal solar wind pressure, the magnetosphere extends roughly 60,000 kilometers toward the Sun. During a moderate geomagnetic storm, it can compress to 40,000 or 30,000 kilometers. During the most extreme events in the recorded historical record, events like the Carrington event of 1859, it has been modeled to compress below 20,000 kilometers. That puts it below the altitude of geostationary satellites, which orbit at approximately 35,186 kilometers. When a satellite that is normally inside the magnetosphere suddenly finds itself outside it, it is exposed directly to the solar wind. It loses the protection it was designed to rely on. The radiation environment changes. The charging environment on the satellite's surface changes. Onboard electronics that were engineered to tolerate a specific radiation threshold are now operating outside that threshold in real time, with no warning, with no ability to shield themselves retroactively. There's something else happening at that velocity that most coverage has not addressed. Stay with me past the 4-minute mark, because what comes next is the part that explains why engineers at NOAA and at the European Space Agency are not calling this a standard storm event. The plasma cloud itself. The physical size of the CME is being described in terms of multiple Earth diameters. To visualize that correctly, you have to understand the scale. Earth's diameter is approximately 12,742 kilometers. Multiple Earth diameters means the leading edge of this cloud spans tens of thousands of kilometers across. And it is not a uniform wall. It is a magnetized structure, a tangle of magnetic field lines embedded in billion-ton plasma, moving as a coherent entity through space. When that structure hits Earth's magnetosphere, what happens next depends entirely on the orientation of its embedded magnetic field. This is the variable that separates a strong storm from a catastrophic one, and it is the variable that cannot be measured until the CME actually reaches disk OVR. Disk OVR, the Deep Space Climate Observatory, is positioned at what is called the L1 Lagrange point, approximately 1.5 million kilometers from Earth, directly between Earth and the Sun. It is Earth's only real-time upstream solar wind monitor. Everything passes through that point before it hits Earth. When a CME reaches ds-OVR, it begins taking measurements. Velocity confirmed, density confirmed, and most critically, the orientation of the embedded magnetic field. If the magnetic field in the CME is oriented southward, pointing opposite to Earth's northward magnetic field, the two fields connect. This is called magnetic reconnection. When it happens, it opens a channel directly into Earth's magnetosphere for the solar wind to pour through. Energy floods in. The magnetosphere begins to ring like a struck bell. Electrical currents in the ionosphere surge. Those currents induce voltage in long conductors on the surface, power lines, pipelines, rail systems, anything that runs for hundreds of kilometers without interruption. The induced voltage can overwhelm transformers. Not all transformers, not all grids. The vulnerability is highly geographic. High-latitude regions like Canada, Scandinavia, and parts of Russia face significantly higher risk because the induced currents are strongest near the magnetic poles. But the cascade effects do not respect geography cleanly. A major transformer failure in a high-latitude substation does not stay in that substation. Here is the ds-OVR warning window math. The L1 point is 1.5 million kilometers from Earth. At 1,293 km, the CME reaches ds-OVR and continues to Earth in approximately 15 to 60 additional minutes, depending on the exact geometry. That 15 to 60 minute window is the entire operational response time after the magnetic field orientation is confirmed. That is when operators finally know whether this is a glancing blow or a direct hit with a southward field. And 15 minutes after that, it is already happening. Consider what 15 minutes means operationally. A power grid operator receiving an alert at 2:17 a.m. has until 2:32 a.m. to decide which circuit breakers to open, which loads to shed, which protective relays to arm. That is not a decision that gets made in 15 minutes without pre-positioned protocols and pre-authorized action chains. If those protocols exist and are rehearsed, 15 minutes is survivable. If they do not exist, if the decision requires human approval chains, regulatory sign-off, or interagency coordination in real time, 15 minutes is nothing. Now for the piece that most of the coverage has buried in paragraph 7 or left out entirely, the ds-OVR satellite itself. ds-OVR is not new. It launched in 2015. Before ds-OVR, the primary L1 monitor was the Advanced Composition Explorer, ACE, launched in 1997. The combined operating life of Earth's L1 space weather monitoring has been just under 30 years, covering a period of moderate to elevated solar activity across solar cycles, 23, 24, and now 25. In those 30 years, the systems have worked. They have detected storms, given warning, and allowed response. But ds-OVR was not designed to be the last line of defense indefinitely. NASA and NOAA have been discussing a follow-on deep space climate observatory, a next-generation L1 monitor, for years. As of 2025, a replacement is in development, but not yet operational. There is no redundant L1 sensor. ds-OVR is the only instrument between Earth and a CME at this velocity, and it is a decade old. Now here is the moment you stayed for, the part that reframes everything else in this video, the Carrington event. In September 1859, a CME hit Earth so powerful that telegraph operators across North America and Europe reported sparks jumping from their equipment. The aurora was visible as far south as Cuba and Hawaii. The geomagnetic disturbance was so extreme that some telegraph lines operated for hours without battery power, running purely on the induced current from the storm. The Carrington event is the reference point for worst-case solar storm modeling. Scientists estimate it produced a geomagnetic disturbance roughly 5 times stronger than anything recorded in the modern instrumental era, and here is the detail that matters for right now. A Carrington-scale CME at typical speeds would arrive in 3 to 4 days, enough warning to potentially respond. Carrington-scale CME at 1,293 km arrives in 1 to 2 days, with a 15 to 60 minute final warning window. The storm does not become more destructive simply because it travels faster, but the response becomes dramatically less effective. In 2012, a CME estimated to be Carrington-scale in intensity was launched from the Sun. It missed Earth by 9 days, just 9 days of orbital geometry, separating modern civilization from the largest geomagnetic event in 150 years. NASA scientists calculated afterward that if it had been aimed at Earth, it would have caused damage estimated in the trillions of dollars and years of recovery time for affected regions. That was 2012. That CME was not traveling at 1,293 km/s. So where does this specific event, the one currently in transit, fall on that scale? The honest answer is that the final severity depends on three variables that converge within that 15 to 60 minute DS-COVR window: the precise velocity at impact, the density of the plasma cloud at Earth's position, and the magnetic field orientation. All three are measurable. None of them are confirmed until the CME reaches L1. What is already confirmed is the velocity, 1,293 km/s. That number is not projected. It is measured from the moment of ejection and tracked through transit. And that velocity alone places this event in the top several percent of all CMEs ever recorded. The historical distribution of CME speeds clusters heavily below 800 km. Events above 1,000 km are statistically rare. Events above 1,200 km are events that solar physicists remember by year. NOAA's Space Weather Prediction Center operates on a G scale for geomagnetic storms, running from G1 to G5. G1 is minor, some grid fluctuation at high latitudes, minor satellite orientation effects. G5 is extreme, widespread voltage control problems, protective systems tripping out of service, complete HF radio blackout on the sunlit side of Earth. The strongest modern storm in recent memory, the Halloween storms of October and November 2003, reached G5 briefly, knocking out power in parts of Sweden and damaging or destroying dozens of satellites. That storm's CME traveled at approximately 2,000 km at its peak, but the plasma density was different, the field orientation was partially favorable, and the warning window was longer. Every parameter matters. Every variable interacts with every other variable. The 1,293 km figure is the known. The rest is still resolving as the plasma cloud crosses the interplanetary medium toward the one instrument that will tell us what we're actually about to face. The promise at the beginning of this video was to explain why this is different, not just faster. Different in the way that collapses the response architecture. That architecture, DS-COVR, NOAA alerts, grid operator protocols, satellite safe mode procedures, was built around a certain minimum warning time. The warning time for a 300 to 500 km/s CME is long enough that it feels like preparation. The warning time for this event, once DS-COVR confirms the magnetic field orientation, is measured in minutes. The architecture does not change between those two scenarios. The time does. Here is the sentence that closes every loop opened in this video. The storm is not the worst-case scenario. The worst-case scenario is a storm of this velocity with a Carrington scale intensity, hitting during a period when the infrastructure warning systems are already at their operational limits, and the response protocols assume a warning window that no longer exists. We are not at that worst case today. The 1,293 km/s CME currently in transit may produce a significant geomagnetic storm, a G3 or G4, disruptive but manageable. It may produce a G5 if the magnetic field orientation is unfavorable. It may produce less than expected if the plasma density drops during transit. The physics will resolve, the instruments will measure, the alerts will go out in the 15 to 60 minute window that DS-COVR provides. What does not resolve, what this event has already permanently added to the record, is the velocity data point. Another CME has traveled at 1,293 km from the sun to Earth's doorstep. And every space weather model, every grid resilience protocol, every satellite hardening standard will be updated to reflect it. The question is whether those updates happen before or after a storm at this speed produces consequences we do not have time to prevent. The math on warning time is not forgiving. The infrastructure built around that math is not flexible. And the sun, which produced this CME and will produce the next one and the one after that across the remaining years of solar cycle 25, does not adjust its schedule to match human response timelines. If this video changed the way you think about what space weather actually means, not as a science story, but as a systems problem with a real infrastructure answer, share it. The people who need to understand this are not only the ones already watching space weather channels. They are the ones who do not yet know there's a 15-minute window. Subscribe if you want to understand the next event before the headline tells you it already happened.